I'd like to give everyone just a warm welcome to the case seminar series. We are really lucky to have Dr. Arpan Biswas with us, who is currently a postdoc at Oak Ridge National Lab. And as they just mentioned to us, will be starting a faculty position in February of next year, alignment and robustness towards materials research and discovery through really two major thrusts. One is autonomous microscope platforms with advanced Bayesian optimization methods. And secondly, physics-informed deep learning models for improved microscopy data analysis. With that, I'd like to give a warm welcome to Dr. Arpan Biswas, and feel free to take it from here.
Thank you, Elder, for the nice introduction, and thank you, Samner and Marcus, for the platform to present my talk. So let me just share my screen. Sorry, it's already shared, so let me start. And yeah, so thank you everyone for attending. So my name is Arpan, and currently I'm working at Oak Ridge National Lab as a postdoc, and I'll be soon training in University of Tennessee, Knoxville as a research faculty in 2 months. So today I'm going to talk about the research that I was mostly involved during my postdoc tenure in Oak Ridge National Lab for past 2.5 years, which entitled about human in the loop Bayesian optimization to improved AI alignment in single multi-objective and multi-fidelity autonomous experiment. So let me begin by acknowledging the whole team. So this was a big collaboration between people from Oak Ridge National Lab, from University of Tennessee, National Cheng Kung University in Taiwan, and also Pacific Northwest National Lab. I'd like to thank everyone here for their collaboration and helping me in this research. So in why I generally sit in the Center for Nanophase Material Science Department in Oak Ridge National Lab. Here you can see in Oak Ridge at the top of the mountain, very nice place to sit. And in our lab, we have two groups of scientists, generally people who are mostly focused on the theoretical aspect of the material science. They are focused on mainly exploring the different classical physics model or the theoretical simulation model in order to come up with the theoretical discovery. And then there are some scientists who helped in the experimental aspect of the material science. For example, running different microscope system, for example, the SPM, STM experiment in order to learn different structure, material property relationship and discover by self. So if we actually try to categorize those two aspects of the study, we can fall into the expensive system. So what I meant by expensive system is any system where you have the cost or time of experiment is high, and generally you have a black box objective and constant, and the black box meaning there is no mathematical equation that can directly tie up between your input and the output of the equation. And because of the expensive nature of the problem, generally you have a limited resource of the data availability, and often in those kind of exploration, like for example in exploring the physics model or the exploring the when we try to learn the structure material property relationship over the vast material space, then generally the design space are very large in order to explore. So we call this whole system as kind of like an expensive system, and how uh, AI can apply to this expensive system, and that is my role basically to apply this AI into the expensive system to discover, to accelerate towards the scientific discovery. For example, we can generate a lot of material images from different microscope. Now, to learn or to discover the physics behind those complex images, we will need some AI capability to actually make that, to interpret that complex images into a simplified one. In other example, when we try to do some experiment, the AI can really help us to tell us like what experiment we should run in order to get to our learning objective and what experiment we should not. So thereby we can reduce the cost of overall running the experiment, and thereby we can accelerate the process towards the discovery. Now, the the challenges that I will focus today is about the AI alignment. So before going that, let me go through what do I mean by the AI alignment. So let's say as a domain scientist, I want to learn, I have a learning objective. I want to learn some material property, structure property relationships. So I can provide that knowledge to the machine learning policy as the task to the AI, and what I am expected that the AI provide me a desired outcome. That we can call as a perfect alignment. And regarding the alignment, something that we need to be noticed is that the result does not provide any violation of the known physics law. And in, for example, in terms of the autonomous experiment, it is actually providing us the preferable experiments that is going to increase our knowledge as the towards our learning objective. Now, the to getting this collaboration between the domain scientist and the AI, which we call the AI alignment, can be very challenging in most of the situation. So to motivate that, here is one of the examples that has been done by the people from Argonne National Lab. So what they try to see is the number of AI integrated paper for different domain science problem. And here you can interestingly see is that the number of AI related paper with the material science domain is probably the least. And this is the potential research gap that we, as the team at Oak Ridge National Lab, trying to solve and trying to explore more and more that how can we make use of the AI in order to solve different problem in the material science. So before going there, the first question that we try to ask ourselves that what is the challenges in the classical AI in order to achieve that? So what's the limitation? Though as I said that in exploring this expensive system, the first limitation is the lack of a large available data set that we don't have that we can train with a classical AI. So we don't have a large amount of data set that we can train a classical AI to perform better. Also, the classical AI does not have the domain knowledge that a domain scientist know. And the reason why the classical AI came into place is to keep the human out of the loop. So basically, it has a very rigid architecture where as a domain scientist, whatever you learn during the course of the experiment, you don't have the flexibility to incorporate that learning to the AI training process such that it trained well. So so today I'll talk about more on how on few of the case study that we have worked on how to solve the AI misalignment to such experimental study, and that can be from the exploring the classical physics model to different complex microscope experiment. So to go back into the history of how the experimental workflow started, we started with a classical manual experiment. So basically, as a domain scientist, you want to learn something, for example, a structure material property relationship. You have the full control with the manual experiment. You have the full control about what experiment you want to run. Obviously, because of that, it is fully aligned, but it can be extremely slow to the point of infeasibility in most of the cases. One such motivating example that I can talk about is so this is a case study where we run when we scan a material sample and we want to learn different material structure property relationship through experimenting through the microscope. Now, this is an example of the SPM microscope in our lab. And this is a scan image of a material sample that we did over the SPM microscope. Now, so this particular image is a 256 by 256 pixel. And at each pixel, you can characterize and generate an experimental data. For here, it's a spectral structure, which will give a lot of information about the material property. Now, let's say as a domain scientist, I want to learn a specific structure property relationship, basically try to find the region which has a high hysteresis loop area. The first question that I need to ask, like why I need AI to do so. Obviously, I can I can go on and characterize each and every point and I can get my learning, right? However, to characterize a single point or the single pixel, it will take about 5 seconds. So in this particular study, if I want to characterize each and every pixel like an exhaustive search, it will take me about 4 days. So the question is, if I tend to block a microscope in the lab for 4 days, the next time no one is going to let me in into the microscope. So the question here is that can we accelerate the process of our learning through the AI? So to do that, a famous review paper that came into place is by saying that taking human out of the loop through the process of Bayesian optimization. So what they propose is basically a fully automated self-driving experiment where, as a domain scientist, you provide the learning objective to the machine learning policy, and the machine learning policy will autonomously explore based on your learning objective and guide through the experiment to give us the learning that we are seeking. Now, when I talk about autonomous exploration, basically I'm focusing on adaptive search, where it will only explore through few of the region in the overall image space and get to the learning that we want. So to talk more about how the Bayesian optimization workflow happens, basically, as I said, that we have a learning objective. For example, here, as I said, the example of maximizing the hysteresis loop area. So I want to learn the region where it has a higher hysteresis loop area over that image space. So that will be my objective about maximizing hysteresis loop area. Now, as I pass that learning objective into the machine learning policy, overall, what it does, it will tell to the microscope like where the experiment or which experiment we need to do. And then once the microscope run that particular experiment, the result will be feedback towards the machine learning policy and it gets updated. So it's a kind of closed loop system where at one point the machine learning tells us what experiment we should run, and based on being updated by the new result, it will relearn and it will tell that what's the next experiment we should learn till we attain the convergence. Now, this overall setup of Bayesian optimization comes from the Bayes theorem. Now, I'm not going to talk in details about the statistical concept of the Bayes theorem, but what I'm trying to focus here is this particular function f, which is the black box function, and that is the function that I'm talking about maximizing, let's say, maximizing hysteresis loop area. Why it is black box? Because as I said, that to come up with the loop area, there is no mathematical equation that you can tie up between your input, for example, the image location, to the output, which is your hysteresis loop area. And you have to run through the SPM experiment and the characterization in order to get that value. It is expensive because, as I said, that you need to go through the experiment or the characterization in order to get that value, which takes time. So the time is the expensive nature of this system. So what it does basically in the Bayesian optimization, to optimize this kind of expensive black box function, what we do, we replace this function by a more proxy, cheaper model, which we call in one way as a posterior model, or generally we feed that with a Gaussian process model, which is a statistical cheaper model. So what it does basically, uh, few number of experiments that you have run, based on that it will give us the knowledge about the functional outcome or the experimental outcome about the region where you have not run the experiment. So it will give you the mean value as well as a measure of uncertainty, like how certain we are that about that experimental outcome, about the particular region where you have not run the experiment. So here in this picture, you can see these three dots are basically the region where we have run the experiment, for example, and the uncertainty near that region goes to minimal, and the uncertainty grows over the other region where you have not run the experiment. So this particular the way that GP model fits actually helps to do the next task of the Bayesian optimization, which is the acquisition function. So what the acquisition function generally does, it holds the key to tell to provide the alignment of the human preferred experiment, that what experiment we should run based on reaching to our learning objective and what experiment we should not. So basically, given the prediction model that we can do from the Gaussian process model, for the acquisition function, it think of two things. The first, it try to capture, or it tries to guide to run more experiment in the region where you have a high mean function value. So in this particular image here, you can see this is the region where you have the high mean value. And that is why it asked us to sample in this region at this point. And this is what we call the exploitation. In the next iteration, you can see it asked us to sample at this point, though it is not in the high mean area, but actually in the high uncertainty area. And this is what we call the exploration. So over the years, we have different function which ends up give trade-off between different exploration and exploitation. But ultimately, the catch is what it does, that it try to exploit more and more towards the region of interest. For example, here is the high function value region. So it tries to capture more and more experiment near that region and thereby reduce the uncertainty. At the same time, it also explored to other region and try to find or discover any other region of interest. If it does not find any good region elsewhere, it does not bother to run more experiment in those area, and thereby avoid the redundant cost of experiment. So over the years, in my postdoc here, I have worked and collaborated with people here, basically to integrate Bayesian optimization to different material, to different expensive system for to accelerate material research. For here example, my work with Sumner. So he has developed recently an autonomous PLD chamber for material synthesis. What we want to do is to maximize the Raman spectrum scoring, and we want to optimize the experimental control parameter values in order to get the best material synthesis, material growth. So what we have highlighted here, that when we run the whole system with the Bayesian optimization for 140 hours, we get the better optimal solution than what we had with the domain expert knowledge. And if you can assume, like, if we want to do it in an exhaustively way, even with the GPU facility, we can run 21 experiments per day. So over the exploration space of 4D and 5D exploration space, it will take endless time in order to do an exhaustive search. So how the Bayesian optimization helped in accelerating the material, in accelerating the optimal solution towards the material synthesis. Again, there is a recent work done by Ganesh, a postdoc in ORNL. So he developed the autonomous STM framework, basically to optimize the optimize the control parameter to maximize the scanning property of the material images. So basically, we try to optimize the FFT peak intensity here, and we try to maximize the quality and the stability of the scanned images. The reason, because if we have an optimal scan, we can get a much better quality to find the atom position, whereas you see with a noisy scan, with a non-optimal scan, it provides much bad solution in order to find the accurate atom position. Um, then we have also implemented the Bayesian optimization in different simulation model as well. For example, here I worked on integrating multi-objective Bayesian optimization for ferroelectric anti-ferroelectric performance optimization. Here, let's say we have two targets like energy storage and energy loss, and we try to do a rapid exploration over the ferroelectric electrochemical model and over the multi-parameter and multifunction space, and thereby we find rapidly the optimal solution at different trade-off between our objective function. So Likewise, we can also implement the Bayesian optimization technique to our autonomous SPM characterization problem. So here what we have done, we use the image overall scanned image as our input space, and then the coordinate point that's selected by the machine learning policy, we created a patch surrounding that coordinate point and pass that into the that location into the experiment where to run the characterization. We characterize at that particular point, we get a spectral structure as our experimental data, and then we repeat the process. So because of the high dimensionality of our input space, we actually replace uh, the standard GP model with deep kernel learning. So to give a quick review about what's the deep kernel learning, it is first designed by in 2015. So basically, it tries to handle the dimensionality problem in the input space. So where we first run a convoluted neural network in order to reduce the dimension of the image space, or sorry, the input space, and then we run the GP kernel on top of that. So it gives much better solution than a standard GP kernel. So basically, with that, with the autonomous characterization, now we don't need to go through each and every pixel, but with the learning objective, let's say here is to maximize the hysteresis loop area, it will explore to few location and it will move towards the actual region of interest with just few exploration. Now, on this previous example, what I have shown is a static objective. So meaning during the course of the exploration or the experiment, your objective, learning objective does not change. But there are some instances in our lab where when we try to learn the structure material property relationship, there can be some instances where during the course of exploration, we can find some unique properties that we really want to learn instead. So there can be some time like we want to change our learning objective on the fly. Now the question comes, can the AI help? Can the AI adapt to changes to that learning objectives that we do during the course of the experiment? So in other words, does the traditional Bayesian optimization still provide the human preferred experiment when we have a dynamic objective? Let's look into conceptually what, as an example, that what's the scenario that I'm trying to say here. Let's say that my learning objective at the beginning was finding the high hysteresis loop area. So as it started the exploring, let's say it moved to a completely new location where I see some very unique material properties, for example, the antiferroelectric structure. And as a curiosity driven, I want to specifically now want to learn this particular structure property relationship, and I don't want to explore more onto my previous learning objective. Now, what will happen though my learning objective change, and as I said at the beginning, the classical AI is rigid. I don't have the opportunity to incorporate that knowledge on the fly to the BO, to the standard BO, such that the acquisition function of the BO will explore to my updated learning objective. So what will happen? The AI will break the alignment to my learning objective or to what my expectation as a domain scientist, and it will think still that the previous learning objective as the desirable one, and it will move away to the true region of interest. Now, as I actually talked with the real experimentalist at Oak Ridge National Lab and come across the same problem that I just discussed now, the current workaround is that they need to stop the experiment entirely. They need to redefine the new objective mathematically, something that can be very tricky or challenging because of the very unique structure to define that in a mathematical term. And even when we do, there is no guarantee like once we start the experiment, we can find or we can discover some other unique properties that we want to also incorporate into our learning objective. So basically what in one way, in a simple way, what I'm trying to say is basically this can be very challenging or tedious for an experimentalist to start, stop, and redefine the learning objective every time. So the question comes is, can we do something about it so that we can changes our learning objective as we need on the fly without stopping the experiment and still keep intact the efficiency of the autonomous experimentation? So with that, the first thing that came to my mind is how the Netflix recommender system works. So I assume everyone is accustomed to Netflix, and once you watch the movies, you have a rating system that you can vote like or dislike, and based on that, it gives you suggestion like what movies you might like or you might want to watch. So why can't we adopt the same thing in our microscope system? So with that, we developed the Bayesian optimized active recommender system in microscopy to improve the AI alignment, particularly when we have changes in our learning objective on the fly. So how it work? So let's say we scan a new sample of material. We don't know anything. We don't need to form any learning objective. We just pick a point to do a characterization just randomly. So let's say this is a point I do characterization. This is the experimental result that I got. And then on the fly, I have the opportunity to access the experimental results. Let's say I provided a negative assessment to that. Now, based on my assessment, it will explore to another location. Let's say now with this experimental result, I have a positive assessment. So as soon as I have some positive assessment, I have a learning object to explore. Now, let's say it moves to another location, and once I have the experimental result, I want to give more preference to this particular learning object, to this particular experimental data. So I can provide assessment with give preference, or we give with voting preference to particular experimental data, and that will reshape my learning objective that I want to learn. Now, let's say over this early exploration, assessment-based exploration, it moved to a another location where I find a very unique structure which does not has any resemblance to whatever I found earlier. And and let's say that as a curiosity driven, I want to explore this newly found structure. So on the fly, I have the ability to deselect all my previous positive assessment and can start a new assessment. And that will also reshape my learning objective on the fly. So with that, with the early exploration, we can kind of scrap through the learning objective and define the learning objective on the fly with the voting preferences, as well as if we find something unique, we can include that into our learning objective. Now, and in as soon as we run some of the assessment, there would be a point where we can satisfy that this is the particular learning objective that I want to do a structure property relationship through autonomous exploration. And then we can switch off to the completely autonomous exploration from the human based exploration. And then and then the AI will know like what is the latest learning objective that the human or the domain scientist prefer, and it will then we can get to the human out of the loop, and then with autonomous exploration now it will keep the alignment and it will flow through the the, uh, the actual learning objective that we want to explore. So to showcase few examples, so this is a case study that we did over the fields in field samples. So the first in exploration we run with assessment, and thereby we develop our learning objective, which is a symmetric loop structure. The reason we want that because it signifies the defect-free region over this image space, and we wanted to learn the region which does not have the defect due to the imaging condition in the microscope. And once we run with the 10% exploration that defines by all these square dots that you are seeing, based on this 10% exploration, we come up with our deep kernel predictive map as well as the uncertainty map. And when we try to validate with the ground truth map, so if we match the yellow region with the red region, and build our square error map, here you can see most of the cases the error are quite negligible here, which shows the model provides a good learning as we just did 10% exploration rather than the full explorative search. We have expanded this whole model in not only in learning a single learning objective, but also the multiple learning objective as well. So here, one of the case study, we wanted to learn the dynamics of the loop. So basically, at some of the region, we can see that with the different loops, there is a shift, and in some of the cases, there are no shifts. So we want to learn these two objectives jointly, and also find the interaction between them. So we feed that with our multi-objective Bayesian optimization. Again, we run the first 1% exploration with the assessment, and then run the fully autonomous with 10% exploration. And then we come up with our different optimal solution at different trade-off between the learning objective. So I'm not going to talk in details about how the multi-objective Bayesian optimization works, but generally what we do here, unlike the single objective based Bayesian optimization, here we optimize or maximize the hyper volume acquisition function. So basically, to validate, we combine, we see what is the hyper volume that we reached over our 10% exploration, and compare with the ground truth hypervolume. So we see it's a pretty close match that we have attained with just 10% of exploration. And to showcase the optimal solution that we get at different trade-off, as we can see that at the trade-off where we have no shift, how we increase the trade-off towards the shift, as you can see how the loop dynamics changes as we have different trade-off between the learning objective. So this is one of the edge case study that we did, and the reason because in everywhere I have actually explained this model, the first question that came to me is, what if the domain scientist, or what if someone using the model is not that much of domain experts, or like there can be some error, or someone who is just randomly selecting a point. Because obviously we aim that, or we envision that someone who will be using this model has the idea about what they want to learn, or has the idea about the material properties that will be unique, or that will be beneficial to learn. But there can be some instances where there can be error in judgment. So we have tried to compare the ground truth, where a domain expert is sitting and providing the actual ground truth, and what if someone who is just randomly selecting or randomly voting the point. So what we have seen generally with the random selection, it pretty much matches with the mean experimental data, like the structure of at different pixel, and the mean of all the structure that we generated. So here you can see, and basically it does not fully it still keep the partial information. So the region where you see this blue region are basically the region where the information is still intact with the actual ground truth, and the region which is basically in red, the information is kind of off with the actual ground truth. So here we can see that even with the random selection, or if we few error in judgment, it's not going to impact that much with the ground truth when we try to build up our learning objective. But then we also, for fun, we also try to match someone who is deliberately hacking the system. So it's trying to deliberately try to vote something which is kind of pretty much providing a garbage value, but not randomly. So here, obviously, that is very unusual that would happen, because this won't be someone who will be kind of like anyone can in the lab can able to sit and do that. So obviously there will be someone who is probably not going to hack the system. So in that case, we have seen, like, obviously the error is going to be much larger than the actual ground truth. So, and so to summarize the overall system, what's the system status currently lies. Basically, let's say we start with a new material sample, we scan that into the microscope, and then with prepare our material image space, and then at few location we generate patch. We feed that into our predictive model as a deep learning model, and then with acquisition function that tells us at which location we should trace. And then as soon we have the experimental data, then human on the fly provide the assessment about the experimental data and thereby reshape the target that they want to learn as a dynamically. And then when we when we transfer that into our objective function, basically we do a structural comparison between our current target and the iterative experimental data as along with the human assess reward that has been given to that experimental data. So we pass that objective function value to our existing data, and we re-update our machine learning model with the new data. To learn for the multi-objective study, we implement predictive model each to learn one target, and therefore we build the acquisition function now, which is a hyper volume based acquisition function. And here you can see, like, once we have characterized, we can generate multiple target, each of different structure to learn different material property jointly, and their interaction between them through the human assessment. So in the early part, once the human assessment cost get exhausted, then human goes out of the loop, and we are fully autonomous driven in order to speed up the process of our learning to find the true region of interest. So in my earlier study, what I have focused on, basically, we have a single fidelity model, meaning we are only the BO is only telling us where to run the experiment, and we are just running the SPM experiment overall. Basically, the cost of that experiments remains the same. But there are some instances where even running the BO can be expensive. For example, when we run the PLD chamber, it took 140 hours to run about 120 sample. So if we think of that, we did not attain the optimal solution, we need to run more, it will take more days in order to do so. So in those kind of scenario where it is much more expensive even for a single fidelity BO to explore, then the next step would be like we can go for a cheaper proxy model, which is less accurate to the actual system, but it can give some information, some partial information about the actual system. And thereby we can feed both this model into the Bayesian optimization, and we can attain a multi-fidelity Bayesian optimization structure. So let's look into one example where we actually need a multi-fidelity Bayesian optimization. Here is one example where we want to learn over a 60 by 60 lattice size sizing model. So basically, here in this picture, the region which is highlighted by yellow, it has a particular polarization direction, and then in the other region, it has an opposite polarization direction. And let's say I want to learn the phase transition over the ferromagnetic space. I want to learn the phase transition over running the 60 by 60 Ising model. Now to simulate each time, it will take me about 8 to 10 minutes to do so. So you can think of, like, even if I do a 1D exploration, and if I just run about 50 simulation, obviously that's not going to be enough to get the optimal solution when we explore on 2D and 3D space. It still takes me about 7 hours to run. So we can think of, like, if we want to explore with more dimensionality problem, it will take me much more hours in order to achieve that. So in this particular case, obviously, to get our learning in an accelerated and in a reasonable time, we need to come across a low fidelity model. So one such instance of low fidelity model that we can use is a 20 by 20 Ising model, which obviously is much faster. So it takes about 30 seconds to run one simulation, but it's not that much accurate as a 60 by 60 model. we can think of as a proxy model. So to fit this to high fidelity and the low fidelity model into the Bayesian optimization, we first set up our problem here. As I said, that we want to learn the phase transition, and to learn that, we can transfer our problem into an optimization problem, which is maximizing the heat capacity. So at the point where we have the maximum heat capacity value, that's the point that we are that there is a transition phase at that region. And we are trying to explore over the 1D spin-spin interaction term, but we can also explore in other input space as well. So to expand our single fidelity model that I talked in my previous example, where we had the SPM characterization experiment, we just have single fidelity. The BO only tells us at which location we should run the experiment. Here we have a multi-fidelity. So the BO, everything remains the same. The only thing is the acquisition function not only tell us that what location we run the simulation, but will also tell us that at which model we should run the simulation, whether it should be a low fidelity model or whether it should be a high fidelity model. So when we run the exploration of our Ising model problem with this multi-fidelity Bayesian optimization, so remember, this is a standard multi-fidelity Bayesian optimization. We don't have any kind of human in the loop or interactive way. So we see the result after running for 25 iteration. It did not give good result actually. The reason because you can see it explored a lot of time to some bad region in order to learn something, but it didn't explore that much of the good region. That's one thing. The other thing is that it is advising to explore with the high fidelity model to some bad region as well, which is even worse, because here we are spending a lot of cost in order to explore with the high fidelity model. So the question comes is that with the autonomous exploration, it did not actually give a good amount of exploration that that the human or the domain expert needs. So again, it comes to the human preferred experiment. So looking into this exploration, it does not give a we cannot say that it actually provide us a good alignment to the human preferred experiment. So thereby, what we propose here again with some human intervention. So obviously, the intervention here would be quite different to the Bohr's model that I talked about. But the idea would be is that the human can guide based on the knowledge that they gain during the course of exploration to better to better tweak the AI in order to get a much better search direction than what it is doing in an autonomous way. So what we build is an interactive multi-fidelity Bayesian optimization. We develop an interactive policy term where we can change a few things. So the first is the parameter space. So what basically we can see that over the course of our learning, we can get some idea like what would be the good region to explore and what is the bad region that we can avoid. So the human can provide that knowledge so that the acquisition function does not bother to explore those region and completely cut off from that region and going forward. And then also next we can change is the surrogate model. So basically when we start, we don't know anything about the function form. We come up with the standard zero mean standard zero mean Gaussian process model. But then when we have some exploration done, we can get the idea about what could be the structural form, what could be the functional form of the true functional form. And we can use that knowledge as term in the physics into the GP as a method of the structured Gaussian process model. In this particular case, once we know from the high fidelity exploration that the function form is kind of like a power law system, so we can provide that prior belief as the prior law function into the mean function of the GP. as well as we want to find where is the maximum point lie. So obviously we don't know the exact location, but we can estimate the exact location from our low fidelity information that we can input into the mean function of the GP. So this we can develop our physics informed knowledge into the GP, and this was first developed by this was already previously developed and designed by Maxim Giatidov in 2022, and which is a good thing in order to learn the GP in a better way, where we can also incorporate the physics knowledge into the system. So the next, what we can also change is the acquisition function. The reason, because what we have seen that when we try to start the exploration, often we need to have more low fidelity exploration, because the low fidelity exploration is going to give us more idea about where are the bad region. But then when you start exploiting over the course of exploration, you will need more high fidelity exploration to get more accurate on the true optimal solution. So we and with the fixed kind of trade-off that we have in a interactive in the non-interactive way, we can actually make a dynamic trade-off between the high fidelity and the low fidelity exploration through the human based knowledge, like where the exploration or where the preferences need to be shifted from from low fidelity to high fidelity. So we can do that on the fly through the human preferred knowledge as well. And lastly, we can increase or also decrease the cost convergence based on the monitoring of the human that where if the optimal solution has made. So this is one of the case study where we actually run the exploration through human intervention. So we start off our exploration with the same initialization that we did in for the non-interactive term. And then we find after 6 iteration looking into monitoring into the system, that this is the region where we're likely to find more good solutions. So we don't want to explore or invest more point in order to explore to the other regions. So we kind of increase our resolution for exploration, and now we incorporated the GP with the physics given information about how the function form would look like and where likely we can find the optimal solution. And as you can see, we are gradually decreasing the cost ratio between the high fidelity and the low fidelity, and thereby gradually we are driving more for high fidelity exploration than the low fidelity exploration, because we want to be more precise exactly where the optimal solution lies. So then after 12 iteration, we also again changes our input. Again, the human intervened and guide the exploration of the BO. And then after 24 iteration, which is exactly the same number of iteration that we did over the non-interactive BO, we find uh, uh, so we find the better solution at this location. As you can see, the maximum heat capacity value is much higher than the heat capacity value that we attain from our classical multi-fidelity Bayesian optimization. The reason we got that, because this is the information that lies for the low fidelity model. So basically, this is the region which shows for a low fidelity model, it has the optimal solution, which is actually not accurate, but the accurate optimal solution lies over here, and that we get through the better interaction or better human intervention into the model. So to summarize, in both of my case study, what I started with the motivation of having an aligned experiment through the classical or manual experiment workflow with an exhaustive search, but obviously with that, though it is aligned, it can be a very expensive to the point of infeasibility, as I showcased in all of my example, that why we cannot go for an exhaustive search. But then when we try for a fully AI driven exploration, we can see that it can be misaligned, it can differ to the real human preferred experiment or the actual learning that the human should be on. So here what I present today is kind of like a best between the human knowledge as the A and also the AI exploration. So we can have a partial human intervened automated experiment which keeps the alignment through human guidance, and it's still cost effective because of the AI exploration in most of the cases. So here what I am trying to focus is the minor intervention of the human, so which will only do the high level task, and all the tedious decision that used to do in the manual experiment will be still running by the machine learning policy in order to speed up the process of experiment. In other way around, what the human intervention aim for is try to improve the search direction of the AI in order to get to the true discovery. And the machine learning will still keep intact the speed of the discovery that is known for. So this is one of the video that I wanted to put, basically how we are providing the voting into the system for our board model. And then this is a real case study where we just run 1% exploration along with the assessment, and overall it took 1 to 2 hours, and based on that we come up with our structure material property learning. And you can think of like, had we have to do it for the exhaustive search, it would take me days in order to achieve that. So so what's the scientific impact in the cases? So with the with the AI, we still preserve the efficiency or the speed in the exploration or the on or running the experiment. And but with the human intervention, we give a better chance to attain the potential true discovery by running new type of exploration or new type of simulation or new type of experiment, and therefore we can get to a the discovery of better structure property relationship learning. So with that, I'd like to end my talk. And if you want to learn more about this project, you can look into our paper, which has been recently published. And if you want to know about more on the coding side, you can look into my GitHub page and feel free to ask me anytime. And lastly, I'd like to thank the entire community for giving me the platform to talk about our research. Thank you, everyone.